Our final titration curve is that of polyprotic acid. So yes, it looks very alarming, but just know you're going to be able to do these actual calculations in lab with experiment 18, which is coming up soon. Okay, folks? Now, this titration curve is going to represent the titration of 40 mils of a 0.1000 molar H2SO3 solution with a 0.1000 molar strong base NaOH. And so our example of a polyprotic acid was definitely H2SO3 Jean Grey. And we know that once Jean Grey was going to donate a proton, that proton is going to have one, or the first Ka1, okay? And that Ka is going to be the largest Ka, and usually the Ka that we focus on when we're thinking of equilibrium calculations, right? Once a proton is donated, HSO3 minus Phoenix is created. And of course, if HSO3 minus Phoenix donates a proton further, then she will become SO23 minus super Phoenix, which nobody wants, right? And so again, most of the time we're going to see H2SO3, but in the lab, we want to be able to show you how both of those protons are going to be donated. So we start where we always start. We start with the initial pH, okay, of this weak acid. And even though it is diprotic, because there's going to be two ionizable protons here, even though it is diprotic, our titration curve is going to show the first proton being lost and then the second proton being lost. So to get the initial, you're going to get your Ka expression because we're talking about a weak acid. You can go ahead and solve for H3O plus, and you can get your pH just from knowing your H3O plus concentration. And from the curve, we expect the pH to be low because we are dealing with a weak acid. Next, what's going to happen? We're going to be adding in our strong base NaOH. And so we have to get our initial amounts of NaOH like we have before with any weak acid. We also can have a Rice table here to get our new initial amount. Once we have our new initial amount, then again, we can go ahead and use the Henderson-Hasselbalch equation to get the pH. Why can we use the Henderson-Hasselbalch equation? Because we actually have a buffer region here. The buffer region is going to be H2SO3, which is the weak acid, and its conjugate base, HSO3 minus, for this first proton removal or donation. Next, you can get the pH at the first equivalence point. Why is it the first equivalence point? Because we're talking about only one proton at a time. So what does this mean? It means that we're going to have initial amount of our weak acid and of course our amount of OH minus that's added. We can use a Rice table. We're going to be left over with the conjugate base. We can use the Kb value. Sometimes you might have to solve for the Kb value if you were given a Ka, for example. And then what can you do with that Kb value? You can solve for OH minus. Once you know OH minus, you can go ahead and get the POH. And once you know the POH, you can get the pH. Then you're going to continue on, meaning you're going to continue adding strong base so that you can get to the second buffer region. So if we're at the second buffer region, that means we're dealing with our now conjugate acid and our new conjugate base here, which is going to be HSO3 minus acting as an acid, and SO3 2 minus is going to be its conjugate base. And since we have that ratio, that means we can get our initial amounts, get our Rice table amounts, and then with our new initial amounts, we can use the Henderson-Hasselbalch equation to solve for pH. And then we continue to add OH, and we're going to get our second equivalence point. I'll tell you straight up, in the lab itself, it's sometimes very difficult to see the equivalence point for the first proton. It's easier to see for the second one. So sometimes you might end up just doing these calculations 4 through 6, or really 4 and 5 for the lab itself. At this equivalence point, all of the HSO3 minus is used up. And of course, we have SO3 2 minus that's left over. So again, we're going to go ahead and get the Kb value of that SO3 2 minus after our Rice table and everything. That's going to give us the OH minus amount. We can get the POH and then go further to get the pH value. And then finally, our sixth point is going to be excess strong base. So of course, if you have excess strong base, you have to have new volumes, new Rice table. You're going to get your excess moles of your OH minus. Once you have your OH minus and the amount in excess, you can go ahead and get your POH and then finally get your pH calculation. Again, you're going to be able to do these calculations and see this in lab itself. So this is like a mini introduction to that. I finally want to end with amino acids as polyprotic acids because amino acids are made up of amine groups and a carboxylic acid. So they literally have the general formula of NH2, which we know is an amine group from our organic chemistry portion, and then COOH, which we know is a carboxylic acid group. And then also it has an R group. And now there's a distinct types of amino acids with 20 different types of R groups, okay? And of course, they all have that COOH and NH2 with some exception. And that means in one single amino acid, it can act as a weak acid and a weak base. a weak acid from the carboxylic portion, and a weak base from the amine portion. So again, we can look at an example here. When you have a amino acid that's going to be in a low pH environment, you're going to end up having a protonated form of the amine group, and you're going to have a protonated form of the carboxylic acid group. Once it loses a proton, it's going to lose a proton from the carboxylic acid group. And so when you're at a neutral pH, you're going to have a positive charge from the NH3 plus group and a negative charge from COO minus, and they're going to cancel to form a neutral pH. When you go ahead and lose the last proton, then you're going to have the unprotonated or high pH form here, because you're going to have the base form of NH2 and the base form of COO minus, and so therefore you're going to have a high pH or a basic solution. That means that polyprotic amino acids can act as both acids and bases within the blood, for example, helping to keep its pH within a narrow and vital range for effective oxygen transport and, of course, overall health. So in the blood, this is what a normal shaped blood looks like. And of course, this is going to help maintain that pH. If you have a disease of the blood like sickle cell, then the sickle cell anemia patients, the hemoglobin only have 2 amino acids with the neutral R groups instead of a charged group. And so because of that, it ends up changing the shape of the red blood cells, causing this sickle shape and, of course, disease in the body. So that's just one way that polyprotic acids, or at least understanding it, is very important as you're going further, especially if you're getting into biochemistry. In the next part, we get to go further and learn more about aqueous ionic equilibrium.